So in this video, we're going to cover the basic concepts of circular motions. So in these pictures, you can see that there's a satellite orbiting the Earth in a circle, and there's a tall tower, people having a fun ride, and all these little boxes are moving in a circle. And then we have cars in this place in the roundabout, and they're going through a circular motion. And here is a little boy who has a ball in a string, and that ball is going in circle. So how do objects move in a circle? For instance, we have this small ball and a string attached to it, and there is a force acting towards the center of the circle, and that's a force that is keeping the ball in a circle. So we see centripetal force in every object that's going through a circular motion. So here we have a satellite. So that satellite is orbiting around the Earth, and there must be a force, a net force acting towards the center of Earth. And then we have got these fun ride where these boxes where people are in. So there must be a force acting towards the center of this middle part. And these cars are going in a roundabout, so there is a centripetal force acting towards the center. So what is the centripetal force and where does it come from? Centripetal force is not a force itself, but it is a net force. It could be provided by a single force like a tension or friction, or it could be an addition of multiple forces. Some cases it could be weight and tension, or and could be a normal force. So the challenge in circular motion problems is to find what is providing the centripetal force. So in this case, say for instance, we have a centripetal force Fc. Here it's Fc, and here we have Fc, and here is also a centripetal force Fc. But in this case, the centripetal force is provided by the tension in the string. And in this case, the centripetal force is provided by the gravitational force, say Gf. And in this case, again, we have tension, and there could be components of the weight. And the cars in a roundabout, a flat roundabout, the centripetal force is provided by friction, the frictional force. So any circular motion problems, that it's important to identify what is providing the centripetal force, because we need a centripetal force to keep the object in a circle. Then only it can continue in a circle. So in this case, the tension in the string is keeping the object in a circle. So say for instance, while this is going through a circle, we're cutting the string. So what will happen? Where will the object move? Say for instance, if the object is moving in this way, in a circle. So when you cut the string, the object will naturally want to go move in this direction. But because of the pull, it's going in this direction. So if you cut the string, the ball will continue in this direction, which is tangent to the circle. In the same case, the car here, they're going in a roundabout and they're going in a circle. If there's no friction, the car will go straight. Because if there's no friction, there's no force that would keep the car in a circle. And in the same thing for the satellite. If there's no gravitational force, the satellite will go straight. And the same thing for the people in the boxes. If you cut the string, they will fly in a tangent to the circle. So that's what the centripetal force and how it acts. So now we're going to look at the basic concepts that we use in circular motion, and we're going to use it for a uniform circular motion. So if we have an object here and it's moving in circle in this direction, so that object has a velocity v which is tangent to the circle. So if it's center, that's tangent to the circle, and that's a velocity. And that object is also have an angular velocity omega. And we have a force acting towards the center, which is a centripetal force, and that's what keeping the object in a circle. So that object will come here and come here, and it'll keep continuing in a circular motion. And if you look at the velocity, and it's going to be v here and v here, it's going to be constant, and we're going to have the same centripetal force here. So now if we look at the Newton's second law, which is Fc is equal to ma, right? So the centripetal force, which is a force, is equal to mass time acceleration. So what is acceleration here? In a circular motion, if we consider the acceleration as a is given by v squared over r. So v is the linear velocity and r is the radius. So we can say Fc is equal to mv squared over r. So where do we get the Fc from? So Fc we discussed that is provided by other forces. So it could be, say, for instance, a tension or friction, or it could be another force, or it could be an addition of several forces. So instead of Fc, we can say that's provided by other forces. In this case, we say sigma Fx is equal to mp square over r. So all the circular motion problems that we will be discussing further will involve this equation, which is the net force is equal to mass time acceleration. So v is the linear velocity, which is always tangent to this point here. So we discussed centripetal force, we know what centripetal acceleration is, and we know what the velocity is, and also there's an angular velocity. So let's look at some of the basic concepts we need to understand to solve these type of problems. So what is angular velocity? So angular velocity is, say for instance, this is theta. So the angular velocity is the angle a, a particular object traveled in a second. So we use omega for angular velocity. That's delta t over delta, so delta theta over delta t. So if we look at a full cycle, how much angle it covers is 2 pi, right? So we can say omega is equal to 2 pi over t. T is the time it takes to complete the whole cycle, which we call as period. So omega is equal to 2 pi over t. Now we find the relationship between v and t. So velocity, or we should actually use speed, because velocity has got a direction, but the speed is constant. So we're not just looking at the magnitude. So the magnitude of the velocity is the speed, because the speed doesn't change in uniform circular motion, but the velocity change. So the speed is equal to, we can write for the whole cycle is 2 pi r, which is the distance it covers in a circle, divided by t. So if you look at this equation, that's the angular velocity, and this is the linear speed, then we can say that v is equal to omega r. So that's the third one we derived. So it's careful that when we talk about the velocity, that if we are just looking at the magnitude, that's 2 pi r t. But that's actually the speed. But if we are going to mention the velocity, that has the direction as well, but the magnitude is the same. And now we have found omega, we have found an equation for the velocity and also for the velocity in terms of omega and radius. So to summarize what we have looked at now, the centripetal acceleration is given by v square over r is the radius, v is the velocity, and centripetal force is given by mass time acceleration, m time v square over r, and the angular velocity omega is 2 pi over t. 2 pi is the angle it covers in a circle, and the t is the time it covers in a circle. Velocity is 2 pi over t. Again, the magnitude of the velocity is the speed, and but the magnitude is same for velocity and speed. So that is 2 pi over t.
Now let's consider this is a circular plate. So this is a center and it's a plate, but it's a rotating plate. And we have got a child sitting on this plate, and there's another child sitting on this plate here, the same plate at different positions. So the it is rotating with the angular velocity omega. That means omega is same here and here, because after a time t they are coming here, both of them will be displaced by the same angle, right? So it's theta. But how about the velocity? Because we found out that the velocity is equal to omega r. In terms of the radius, they're both different. So this one could be r1 or this could be r2. So the velocity here, if it's v1, if it is v2, we know that v1 is equal to omega r1 and v2 is equal to omega r2. So this is quite interesting. So the same circle at different distances, the omega is same, but the velocity will be different. And how about frequency? Frequency is given by 1 over t. And also, if you relate that to omega, so omega is given by, so omega is equal to 2 pi over t. So we can also say omega is equal to 2 pi f. So that means the frequency also will not change when the radius is not changing. So if omega is equal to 2 pi f, so f is equal to omega over 2 pi. So here we got v is equal to omega r, v1 omega r1, v2 omega r2. So if you want to put the velocity in terms of the frequency, that means v1, instead of omega, we put 2 pi f. So 2 pi f r1 and v2 is equal to 2 pi f r2. So when we are looking at a object here, is in uniform circular motion, the velocity is, in terms of magnitude, it's same. So v here and v here and v here. And the acceleration, here it'll be v square over r, and here it's v square over r. And the same here as well, v square over r. And the centripetal force is the same, which is mv square over r. So is it constant in a uniform circular motion? Is velocity constant, or is the instantaneous acceleration constant? No, they are changing because they are vectors. So the v, velocity v, is changing, and acceleration a, changing. But the magnitude of v is not changing. So the magnitude of v is the speed. So if you want to find the speed to see if it's changing in a uniform circular motion, no. So uniform circular motion is defined as a motion of an object which has a constant speed, that is v. So the speed is constant, but the acceleration and velocity are changing. And the second thing is that we don't need to have a full circle to define a uniform circular motion. So if we have a road and there's a roundabout, that's not a perfect one, but that's a roundabout. So there's a car coming here, and the car will turn here and go here. So if you look at the points here, the car will go through a circular motion where the center of the circle will be here. And then a circular motion here where the center will be here. So we don't have a full circle, but we are seeing there are two circular motions for this car. So in terms of acceleration, you can see that first the acceleration is in this direction, and then the acceleration is in this direction. So if we look at the car and say it's point A and B, initially when it turns this way, the acceleration is this way. But when it goes here after passing the corner, then so this still we have A and B, and the acceleration is this way towards this circle and this circle. So in circular motions, it doesn't have to be a full circle, but we see circular motions in other instances where an object has to go through part of a circle, where we can work out the acceleration velocity using the radius.